So board is on and we are ready to go. All right. So so we'll try again today, to talk about structures. And these are the same structures as what you should have learned in CISP 360. So we're going to get started with the C code, which is already here. I'm going to back out of GDB just so that I can talk about the source code first, and then we'll get into GDB and just kind of notice a few things. Okay, so there we go. And I'm going to change the program just a little bit. This is essentially the same program in the announcement. Um, I have no idea why it is complaining these days. Oh, that's because I forgot to use nvim. Okay, there we go. All right. So line numbers are not showing yet because the projector is not using the entire width. So what I can see on my screen is not being displayed on the projector. There we go. Okay. All right, so line one is a typical header file that I like to include because it includes definitions that will give you integer definitions that is signed, unsigned, and also width dependent. So it's very handy because I want to specify exactly the number of bits per integer in this case. Line 2 to line 6 is the definition of a structure. So we have to be careful about what it means to be the definition of a structure. A structure is like a class. Okay, so for those of you who have taken 400 or 430 even, a structure is like a class. It is a template. It is a type. Okay, so a structure is not a variable. It is not an object. A structure is used to stamp out variables or objects. So right here we have a structure. The name of the structure is X, okay, uppercase X, which has nothing to do with Elon Musk at all. And then it has, confusingly, lowercase x as a member of the structure, lowercase y as a member of that structure, lowercase y is another member, lowercase z is also another member, and then we have main. Main has two variables right now. I'm going to add a third one. Okay. So the first one is v1. Okay. The second one is v2 as for variable. V1 is an actual structure, okay, because it is not a pointer. V2, on the other hand, is a pointer to a struct X. So I'm going to change the program so that it has another variable, which is V3, okay, and V3 is also just a regular structure, and we say V3 dot X equals to V 2 points to X here, and we'll probably do it after the initialization, like so. There we go, semicolon. There we go. All right, so this is the sample program that we are going to use to illustrate a few kind of important concepts in order to implement structures in assembly language. Do we have any questions about the C program? Because if we are not understanding the C program, the assembly code is not going to make sense. Yes. Can you repeat the question, please? Yes. Of what? Nope. Nope. Member Z of a struct X is really just a pointer to a unsigned A-bit integer. That's all it is. Well, it can store the, well, as far as types are concerned, it is compatible with the address of any address of an A-bit unsigned integer. That's all. That's the only requirement for Z is it has to store the address of an A-bit unsigned integer. Yep. Go ahead. That is correct. So V2 becomes a pointer to V1, which is an entire structure. But the pointer is only pointing to the beginning of the entire thing. Okay, so keep that in mind. Okay, any pointer in C++, any pointer in our assembly language is only pointing to a byte. If the structure takes more than a byte, then it is pointing to the very first byte of the entire structure. Go ahead. So, okay, all right, cool. So this program doesn't do anything useful. So if anyone is trying to find meanings in this program, there is none. Okay, the only purpose of this program is to illustrate a few concepts, but those concepts in return are actually really useful. So we'll go ahead and compile and run the program. But for the most part, we just want to use GDB to inspect a few things. So GCC dash G dash O struct.c. It's faster for me to type the command line to compile the program and debug it. Instead of using a what we call a IDE, integrated development environment. There we go. All right, so we just run the code. Okay, it ran all the way to line 17, so every line should be done by now. Okay, so the first question I have is what are the addresses um, that might be important to us at this point? In other words, where is V1? Where are the addresses of the members of V1? What about V3? Okay, what is the address of V3? And what are the addresses of the members of V3? So those are the initial questions because I want to see if there is a pattern. Okay, so that's the first thing that we're going to do. And I'm going to maximize the length of the screens just so that we can look back a little bit further. I don't have to scroll as much this way. Okay, there we go. So I'm going to take a look at, okay, where is V1? So here's an address, okay, it is a 64-bit address, and that's why there's a whole bunch of hexadecimal digits. There are 16 of those. So for the most part, we only have to pay attention to the least significant 2 or 3 digits, okay, because we're writing fairly simple programs, and they're not using a lot of locations anyway. So in this case, V1 starts in an address that ends with hexadecimal 40. Okay, cool. And then we want to look at the individual members. Okay, where are those members? So when you use ampersand, it is ampersand has a lower priority compared to the dot notation, which is member of. So I can actually do something like this. This is implicitly putting the parentheses around v1.x. We are finding the address of member x, which is a part of v1. Okay, so we press the enter key. It is at exactly the same place as the structure itself. Does that make sense to you? That the very first member of a structure has the address of the entire structure itself. Exactly. Just like in an array, members or element 0 is at the very beginning of the entire array. It kind of makes sense, right? Because otherwise, what are you going to use, the memory for at the very beginning of an entire structure? There's no other use for those things except for, oh, we'll just use it to store the first member. Okay. So now we try to look at the second member. Okay. So we look at member Y and ask, where is it? It says member Y is, oh, it's just 1 byte after member X. Member X itself is a 8-bit unsigned integer, which means it only takes 1 byte, one location in RAM. And member Y is right after that. Does that make sense to you? It is contiguous, yes. Are we good so far? And then something does not make sense because now we take a look at Z, okay? The address of Z, which is a member of V1, you go like, wait, that is not 1 byte after Y. It is a whole bunch of bytes after Y. Why is that? Because, okay, very good. It is a pointer. So, but it is not really directly because the fact that it is a pointer, but it has to do with a pointer takes 8 bytes in a 64-bit architecture. Nope, it has nothing to do with what it's pointing to, but it has to do with the width of a pointer. Yes. Nope. Has nothing to do with what it is pointing to. It really is just the pointer itself. It's the width of the pointer that dictates whether it can be right after or whether it has to skip a few bytes, in order to start at a specific location. Okay, so I'm gonna, kind of pause this discussion here in order to give you an idea of why it has to skip a bunch of bytes. And the best way to describe that is to use I'm going to put this into the share folder, just so that you guys can have easy access to it. And I'll use a spreadsheet for this purpose because a spreadsheet can really, I mean, it saves me a lot of time to kind of type up stuff. Okay. So what I'll do is I'm going to, specify some offsets here. 0, 1, 2, 3, 4, 5, 6, 7. The reason why I went from 0 to 7 here is because it takes 7 bytes to make 64 bits. Okay, so there we go. And so here we have multiples of 8. Okay, so we have 0, we have 8, and then we have 16, and so on. Okay, the internally, internal to the processor, a 64-bit processor, which includes the AMD 64 architecture, the ARM 64-bit architecture, and so on. Internally, whenever you want to retrieve a byte from memory, it is always retrieving 8 bytes at a time. In other words, it's always retrieving 64 bits at a time. That's because the D port of the RAM, at least conceptually, is 64-bit wide. You cannot say, oh, I don't need all 64 bits. I just need 8 of the 64 bits. Just give me 8. No, he is 64. Okay, and then the processor can go like, okay, fine, out of the 64 I really just need these 8 over here and do some processing with those 8. Okay, so that's kind of the nature of a wide processor, or a wide bit width processor, as opposed to the one that we use for this class, which is tiny. Okay, it's only 8-bit wide. So this is how 64-bit works. So now if we arrange and go like, okay, this is where member X goes. Okay, cool. Member X only needs 1 byte. Member Y can go here. That's cool. So member Z is a pointer. It takes 64 bits, right? So if you are in the mindset of I want to save as many bytes as possible. I want to pack things as much as possible, then you would have to arrange it like this, right? 1, 2, 3, 4, 5, 6, and then 7, 8. Okay, so the question is, well, that works, right? That's no problem. The answer is you're correct. There's no problem. The problem is about efficiency. It's not about whether it can be done, but it has to do with whether it can be done efficiently. So when you need to get to member Z, now you need 2 memory accesses instead of 1, because the first memory access is going to access everything on this row, which is byte 0 to 7, plus the original offset of 7. So that will get 6 out of 8 bytes that belong to Z, right? A part of it. And then the processor will automatically do this. You don't have to tell the processor for the second access. The processor will then go have another memory access just to get 2 more bytes that belong to the address. So it takes 2 memory accesses to get to a 8-byte item. Is that okay? Now, how can we save time? How can we go like, okay, can we just use one single memory access to get Z? Yes, exactly. So that means, what we do is we say, Z is not going to be here. It's going to be all on the second row. So that means now these bytes over here, right after Y, we have 6 bytes that are not used for anything. It's like, yeah, they're wasted. Okay, in order to uh, optimize memory access, we would rather sacrifice memory locations. So that's the default strategy of compilers in C and C++, and this is exactly how it determines where Z should go as far as the offset from the beginning of um, the structure is concerned. Yes, yes. So, well, actually, it is a little bit more complicated than that, but at least conceptually for our, for this class, each memory access is going to take in all 64 bits or 8 bytes. Even if you only need like one of them, it's going to read all 64 bits because the bus itself is that big. Imagine, imagine you have a bus like a RT kind of bus. There's only one passenger. Well, it's just moving around with a lot of empty seats. Not efficient, but it is more efficient than having to have RT to purchase buses of different sizes. Because most of the time you do have a lot of passengers, it's just occasionally you only have one passenger. So it does not make sense for RT to purchase, a two-passenger bus and then a four-passenger bus and then an eight-passenger bus just for those occasions when you say, yeah, we think this time of the day we're gonna have very few passengers. Yep. It cannot be, yeah, yeah, exactly. These gaps of spaces, cannot be salvaged. So they're essentially lost. Yep. It's not too bad, okay, because these days, we typically have a lot of RAM, so computational resources is no longer a bottleneck for implementation of programs. Many, many years ago, in the 50s and also in the 60s, that's a huge constraint. So at that time, we had mass store was not a problem because we got tape, reels of tape, which is very efficient and both in terms of money and time to store data. But we don't have a lot of RAM because semiconductor technology was way behind actual physical magnetic storage technology at that time. So that means, you have plenty of mass store, but you have a tiny amount of RAM. And people have to derive algorithms to deal with that situation. And that's why we have merge sort. Merge sort is one of those really clever algorithms where it can deal with a huge amount of data using a very tiny amount of RAM, because at any time you only need to store up to 2 records in RAM, even though you might have billions of records to sort. It only needs to store 2 records at a time. So that means the RAM requirement of merge sort is like this much, no matter how much data you're actually trying to sort. Now, you cannot say the same thing about quicksort because quicksort requires everything to be in the entire array. So that means, however number of records you need to sort, they all have to fit in memory. And that is made possible because of the advances of semiconductor, because we can make transistors smaller a whole lot more than we can make little magnetic stripes smaller. And at this point, we don't really use magnetic medium anymore. If you look at all the data centers, they don't use hard drives. They all use SSDs now. Yeah, but they are now used as an archive, kind of mechanism, and not so much as an actual. uh, runtime mass store device anymore. So hard drives is now taking the place of tape drives in the past, and then SSDs are now taking the place of hard drives now. They can be very dense, but they're also extremely inefficient to retrieve stuff. So if you have something that you know that you won't need for a long time, you can put it onto tape. Yes. Hmm? Well, but optical is good too. Optical is actually potentially denser compared to magnetic. All right, so this is the reason why Z is not right next to Y. Instead, it is 8 bytes away from the beginning of the entire structure. Is that okay? All right. So I think that picture kind of helps. This is actually the first time I use a picture to illustrate this, but that's basically what it is. Now, this problem does not exist on TTP because TTP is a byte computer, so we are not retrieving or writing 8 bytes at a time. We're always just retrieving and writing 1 byte at a time, so we don't have to waste space like this. Z can be adjacent to Y, can be contiguous, so we don't have this problem. Okay, so this is one observation that's kind of interesting. What about this? What if I were to ask, what is the size of V1? In other words, how many bytes V1 as a structure is going to consume? No. Um, so look at this, okay? The entire structure starts at 40. Z is starting at 48, but it is also 8 byte wide. So how many bytes total do we need for a for V1 as a variable? It's 10. It's hexadecimal 10, not 10. It's 16 bytes. It is 16 bytes because in the picture here, the structure is going to take up all of these bytes here, despite these are not used. They're still counted. Yep. So in C++ or in C, you can use the size of operator so that you can say, oh, okay, this particular variable is using 16 bytes. Okay, now this is a fairly kind of handy, it's a handy feature. It can be really useful, certain times. All right, so now I'm going to move on and ask, where do I find V3, which is also a structure? That's where it is. And if I were to ask where is V3.Z, what do you think it is? Yep, based on what we know about V1 or members, where we can find the members of V1, now that we know V3 is starting at location blah blah 30, where do we find member Z of V3? It'll be 38. Exactly. Okay, so that means the offset to members across variables of the same structure stays the same. That kind of makes sense, right? Because if that changes, it's like, how do we find things anymore? Okay, um, it's, I mean, C++ is like this. I cannot say the same thing about other scripting languages because they're not structured the same way. Okay, I will just put it that way, which is a very mild way to say it. Okay, cool. So now what we can now do is to go like, okay, so if I were to implement this program in C in assembly, this is what we're going to do. Okay, so we'll take a look at struct C and also to the implementation in assembly. Okay, so I'm going to start with the representation of the structure. So I'm going to say XX is a 0. So by itself, yes, go ahead. Huh? We can do that later. The ordering of label definition really does not matter. Yes. Oh, make the font bigger. Yep, we can do that. Is that okay, or do you need it to be even bigger? All right. All right. So the label uppercase X underscore lowercase x is has a special meaning. It is the offset to find member lowercase x from a from the beginning of a struct uppercase X thing. Okay, let me say that one more time. Okay, the meaning of this label is the offset to find member lowercase x from the beginning of a struct uppercase X construct. Usually a variable, but sometimes it is not. Is that okay? Yes. It doesn't matter because label definition in most assembler uh, can do forward and also backward reference. So it doesn't really matter where you define it. Okay. Okay. So if that is the case, how would I define x underscore y? Yep. So I would do this. And if you are to say, but that's just one. Yeah, it is one. But I like to express the relationship between label x underscore y to the label x underscore x. So that's just my preference is to do things as relatively as possible. So this way, if I want to say, oh, guess what? Member x is not the first member. I want another member to be the first member. I don't have to change all this code. But other times, depending on what kind of modification I want to do, it may not be avoidable. So in assembly, Z is really just your Y1 plus, because in C, excuse me, in TTP, an address is only just 1 byte wide, and we are not dealing with a 64-bit architecture. So the stuff that we talked about a little bit earlier really is not applicable, which makes things a lot simpler. Okay, because otherwise you're gonna go like, oh, are we gonna waste 6 bytes, in order to optimize memory access? No, none of that when we are programming in TTP ASM. All right, cool. And we're going to say, okay, this label is going to be defined to be the number of bytes that a structure of type struct X needs in this case. So once again, I'm going to do a relative thing, which is X underscore Z 1 plus. X underscore Z is the offset to find the beginning of the last member of a struct X, and if I add the size of that struct of that member to the offset, then I get the total size of an entire struct X. So that's how I define all of these labels. So in place of line 2 to 6 in the C code, in assembly, all you can do is to use labels to help you identify where do I find a particular member of a structure. Yes. Yeah, Z is only 1 byte because in TTP an address is only 1 byte wide. Yep. hmm Um, so there's no real actual automatic. Exercise is really just calculating, the total number of bytes that the struct X is going to take. So in terms of memory allocation, we would have some idea of how many bytes should I allocate for, in this case, V1 and V3 in main. So we're going to use that later on. Okay, so the size label is going to be useful when we need to calculate offsets to access my local variables. Question? We have 3 members and each one is 1 byte wide. Yep. So if you have members that are also by themselves structures, then the calculation gets just a little bit more complicated. Or adjust how size is defined. Yeah, so you have to make some adjustments. As much as I want to future proof this code, it is not entirely future proofable, so you still have to make some adjustments. Mhm. All right, so now that we have a structure definition, we can now have the usual entry code, which is no op. this is unnecessary, but it's good to remind ourselves that the stack pointer is register D and it needs to start with 0. And then we have the usual LDIA dot 6 plus, decrement D, whoops, and then we have a STDA, and then we have a JMPI to main. When we come back, it is a halt. So even though by this time, most of you recognize the template of how we call a function, it is still useful and helpful if you remind yourself in your head of what each instruction is doing and why it is necessary. Okay, so other than the no op instruction on line 6 and also the line 7, which is the initialization of the stack pointer, every single instruction is necessary. It serves a purpose in this code. Yes. It, yep. The return address. Yep. Yep. Exactly. So now we move on to main, and once again, I do not write code in a linear way. Um, Apparently, most people say that I also do not think, learn, and teach in a linear way, which is good, bad, and horrible at in different situations. So anyway, but I do encourage people not to do it in a linear way because the non-linear way, which is the structured way, is um, it's less you are less prone to make mistakes using the structure way. At least that is true for me. Okay. Yep. We will get to that point. Good question. Good question, but we will get to that point. So I'm starting with the return instruction. The return instruction is basically saying by the time we get to the end of the whole thing, the stack pointer should once again point to the return address, which was pushed right here. Then I can increment D to deallocate the return address, and then I can continue execution at the return address using JMPB. So once again, even though those 3 lines of code is like a template, okay? It's like, oh, okay, I know what 3 lines of code I need to return. It is still good to remind yourself what each instruction of the 3 is really doing. Okay, so that is still kind of something that you want to keep reminding yourself. Yes. Mm, it is okay. So if you just look at JMPB, all it does is to copy register B to the program counter. That's all it does. Now, if everything works out the way it's supposed to, register B should have the address of the halt instruction here. So by updating the program counter to become the address of the halt instruction, you are now saying, okay, processor, the next instruction you need to execute is the halt instruction. That's the way it works. Mhm. And this is also why, I introduced the actual architecture in this class, before we talk about the actual assembly instruction, because, hopefully you guys, got the time to actually study and understand the architecture. Because if you do understand the architecture, and I just say, oh, we're just copying register B to the program counter, that will kind of give you an idea of, oh, okay, so that means the next fetch cycle is going to go to the address of the halt instruction, take that opcode in, decode it, and the process or the result of decoding, the halt instruction is the effect of actually halting because it's not going to move, it's not going to go anywhere after that point. Okay, so this is the reason why I use my own architecture because you can then really look under the hood and find out exactly what is going on, you know, when the code executes, which I think is important in a class like this, in addition to actually writing the program here. Okay, so now we can look at the offset of the local variables. So v1 being the first variable that we see, it's going to start with an offset of 0. So now we can now say, okay, what about v2? Well, you guys already know TAC likes this approach. Okay, we start with the offset to the previous one, but now we have to go like, we know we have to add something to it, but what are we adding here? In other words, how many bytes is V1 going to use? because we want to define the label main underscore v2 to be the offset from the beginning of the frame to the beginning of v2, which means I need to know how many bytes v1 is going to consume in order to determine where v2 needs to be. X size, very good. That is the reason why I want to have that label v size. Okay, so x underscore size is here. Is that okay? Now, does it stop anyone from saying, oh, but I know exercise is just three. I'm just going to type the constant three here. No, some people would do that, but that kind of code is going to be very what I would call brittle, because the moment I change struct x to have more or less storage, these if people hard code a three in place of exercise, all the places with a three potentially needs to be changed, because just looking at the digit three does not know, you won't know whether it's referring to exercise or something else that also turns out to be three. So having a symbolic name is always helpful because you can fix the symbolic name definition and you're all done. All right. So now we move on to the next one, which is V3. Okay, V3 is right after V2. Okay, so there we go. And in typical tag fashion, we just need to figure out, okay, how many bytes are between V2 and V3. V2 is not a struct X. It is a pointer to a struct X. So we know a pointer to a byte or to an 8-bit unsigned integer is only 8-bit wide. What about a pointer to a structure? Every pointer is 8 byte. Sorry, 8-bit. Yes, 1 byte. Because the processor itself is byte addressable. So that means and there are 256 of those. Okay, so that means I can only have up to 8 bits for a pointer in TTP. Okay, because of the number of locations that is addressable, I can only have 1 byte. So this is just a 1 here. Nothing fancy, just a 1. But I also have LVS. So for those people who are thinking, tag, why do you define LVS to be 0 and then you allocate and then you deallocate, just wasting processor instructions? It's because it is a template that works. Okay. Now I understand, adding 0 is not efficient, subtracting 0 is not efficient, but I would much rather have the code to run correctly first, then I worry about efficiency. Okay. Because if my boss tells me to turn in something, okay, tag, your deliverable is a program that can do blah blah. Okay. I go like, okay, I know how to get this program to work, not necessarily efficiently, but I can get it to work in 2 days. And let's say the program is due in 5 days, okay? So I would work on this program for 2 days, get it to work first. May not be the most efficient solution, but it will work, okay? And then I'll back it up, okay? Check it into GitHub, label it, okay? Make sure I can know it's easy for me to retrieve that version, and then go like, oh, I got 3 more days. So I'm gonna use those 3 days to try to optimize the performance. On day 5, if I can finish the optimization, everything still works, great. I deliver a correct and efficient product to my boss. My boss is going to be happy. If I cannot finish the optimization, because optimization usually is tricky, okay? Usually it leads to bugs of all kinds, okay? I'm not going to get into that. So let's say on day 5, I still could not finish the optimization. Guess what? I still have that working version from 3 days ago that I can turn in. It is still correct. It's just not as efficient as I would like it to be. Now, if I were to tell my boss, I'm sorry, boss, I tried to optimize the program to make it go faster for 3 days, but I couldn't finish it. What do you think would be a typical response from the boss? For what reason? I might be fired, or the boss would probably frown on me, because most bosses only want the program to work. They do not necessarily want it to work in the most efficient manner. So any attempt to make a program easier to read, to make it more elegant, more maintainable, more efficient, may not be met with encouragement. I'm telling you this with as a personal experience. I was never at any danger of getting fired, but my boss said, "Tech, you just wasted your time making the program better." Going like, "You just said it. Yes, I made it better." And I broke his program because he was relying on a an implemented feature in C++, like type checking, when he wrote his own code, and when I do full type checking, in the compiler, his code broke because he was assigning pointers of different types without casting. So my feature broke his code, and he was upset. I go like, so, and then the first thing he said is, take it all back. Okay, do not implement type checking on pointers. I go like, but this is the ANSI standard. I think we should try our best to adhere to the standard that everybody else is using. So eventually I made a switch in the compiler so I can turn it into norm mode. My boss is norm. So turn it into norm mode so it would actually ignore type checking errors. Yeah, fun time, fun time. All right, so LVS is going to be main V3 X size plus because V3 is a structure itself. So that's why in the calculation of how many bytes I need on the stack for the local variables, this is how I calculate the entire thing. All right. So with LVS already defined, now to allocate and to deallocate is something that is super duper easy because we have seen this code many times already. We subtract this much from the stack pointer to allocate, and then we add it back to deallocate. So everything else would just kind of go in between. So you can see that this program, even though the main purpose of this program is to illustrate structure or how to use structures, most of the concepts that we have talked about in the past, they still apply. Okay, so everything is kind of like Lego pieces. Okay, they all connect, which is kind of cool. Okay, I think it's kind of cool. You guys can think whatever you want. Yes. Yep. It is part of the frame. In other words, if you want to look at the frame itself, and I always make what points up to be higher memory addresses and what down to be lower addresses. So after the entire frame is all done, what you end up with is v3.z is at the highest location, v3.y is the second lowest, v3.x is the lower, another one which is lower. V3 takes up only 1 byte. V1.z is here. V1.y is here. V1.x is going to be here. And that's the exact byte arrangement of the frame that is related to the local variables. So if you want to also include the return address, it's going to be here. The return address to the entry code is going to be here. So this is the entire call frame of main. Obviously, this is going to be location FF. And the stack pointer is pointing to the very last item that is allocated. So after all the allocation, the stack pointer D is pointing to the base of the frame, which also turns out to be the address of V1, which also turns out to be the address of member X of V1. So are we doing okay so far with this? I think the picture is helpful, especially for people who are visual. You can wait until I upload this code. You can also just kind of copy that onto your own notes, draw a little picture. Sometimes the action of drawing a little picture also helps. All right. Shall we continue with the implementation of this program? Okay. All righty. So let's move. Let's move on to line 12 of the C code, which is here. Okay. So we are copying the address of V1 to V2. Okay. So how do we do this? LDIA main underscore V1 add AD, and then we do LDIB main V2 add BD STBA, done. Attack. You just talked about structures today. I cannot understand this kind of code that quickly. Structures have nothing to do with these concepts. Okay? Calculating the address of a local variable or a parameter has nothing to do with what the local variable is. It can be a bit unsigned integer. It can be a signed a bit integer. It can be a structure. It doesn't change how we calculate the address. As long as it is on the frame, I have a label that is defined to be the offset to that item from the base of the frame, and I know where the stack pointer is. That's how we do it. Okay? So that means I'm not going to explain these 5 lines of code. Okay, you probably, if you're not understanding these 5 lines of code, it is time to review some of the previous concepts, because the way we calculate the address of a structure that turns out to be a local variable does not change. It does not. It's the same as the way we have always been calculating the address of anything that is on the call frame. Yes. Yep. 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 So the most important part is to remember that at this point, the stack pointer is pointing to the base of the entire frame. And the label main v1 tells me the offset in number of bytes of where I can find v1 from the base of the frame. So I need two pieces of information to find v1. One is the offset from the frame, and then the second one is where's the frame. The stack pointer tells me where the frame is. So that's how we do, this calculation. Now, the next one I have to spend a little bit more time because, this one does relate to the concept of a structure. So the first one is easy, okay? The right-hand side of line 13 in C, that's just 20. We'll do LDI into register A, done of for the right-hand side. The left-hand side is a little bit more involved. So the first thing is, um, I need V2 first, okay? Because I need to get to V2 before I can get to a member that is pointed to by V2. So the first thing, this is also the first time in the history of me teaching this class, as far as I can remember, that I emphasize this part, okay? I do teach this every single semester, but this is the first time I've emphasized it first, is how do you read the left-hand side of line 13 in C? Most people just goes like, it's v2 point to y. Okay, well, they're not wrong. Okay, but it's not very descriptive. Yes, it is the reference. Okay, the way I would describe the left hand side on line 13 is we want to get to member y of the structure that v2 points to. Yes. Yep. Yep. Exactly. Yep, exactly. So let me explain why what I just said was, well, at least what I think is important, okay? Because when you describe the left-hand side of line 13 the way that I did, okay, I need to look at the time, we got plenty, which is member Y of the structure that V2 is pointing to. That alone tells you the dependency of things, right? Because every time you see blah 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 of blah blah blah, okay, okay, I'll say in a different way, blah 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 of yada yada yada, okay. Which one do you need to figure out first? The blah 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 or the yada yada yada? The yada yada yada, right? Yep, exactly. So that means the if you describe something with precision, the way you describe it is already giving you the sense of dependency. Once you understand the dependency, then you know what you need to figure out first. Then you have the order of operation. You're no longer lost. It's like, okay, I got a bunch of stuff that I need to figure out, but I don't know where to start. No, you know exactly where to start, what is the next step, and what is next to it, and so on. So this is after many years of doing this without knowing what I'm doing, because I was doing this kind of intuitively. Now I can spell it out. Okay, it's kind of like a dependency-based way of thinking, of problem solving. Is you're not even solving the problem first. You're just trying to figure out dependency. Okay, what depends on what else? And then once you understand all of that, you go all the way to the root of the dependency chain, and you go like, okay, I'm going to address that first, because it makes no sense to address anything else. Is that making any sense? I hope so. Okay. Um, so that's how I recommend people to do this. Okay. So that means I have to find V2 first. Okay. So let's go ahead and find V2. We already have some code up here that finds V2, but we'll go ahead and do that again. So we load this and then we add that. Okay. That would be the address of V2. Now we have V2. So V2, the pointer to a structure, is now in register B. In other words, register B is now containing the address of the first byte of the structure that I need to access. Okay, so the next step is to say, okay, I know where the beginning of the structure is, but I don't want to get to the beginning of the structure. I need to get to a particular member of that structure. Do we have a symbol? Do we have a label that is defined to be the offset from the beginning of the structure to member Y in this case? X underscore Y. Very good. Okay. So now I can say, let's blow another register just to store that, X underscore Y. And then we just have to add those two. Okay. Which way you add doesn't really matter. Okay. Because they're both just kind of scratch registers. So I'm going to add C to B so the end result is stored in B. So now instead of B having the address of the structure, B now has the address of member Y of the structure that I need to access, which means I only need one more instruction to finish this code. Okay, I just need a store. B is already the address of member Y of V2, so I just need a store. A already has a constant of 20. We are now done. We are done with line 13. So the sequence of code is important, okay? But I think more importantly is how do we solve the problem, okay? How do we look at the left-hand side and step by step figure out, okay, I need to figure this out first, then I need to figure this out, then I need to figure this out. So I think that part is equally important compared to the actual sequence of instructions. Is how did I come up with that sequence of instructions? Are we do okay? Ready to move on to the next one? Okay. So the next line is line 14, which is kind of the same thing, but not exactly the same thing, because this time I am storing a 10 to member X of V1, not what V1 points to, because V1 is not a pointer. V1 already refers to the structure itself. Okay, so now we're going to take a look at the code and see how that might be a little bit different compared to lines 29 to 35 in the on the assembly side. Okay, so the right hand side is the same thing, easy peasy. So LDI A10, okay, done. The left hand side is like, okay, so how do we say line 14? Member X of V1, okay? Well, we still have to find V1 first, okay, according to what I just said, and then we can find member X of V1. Okay, fine. We'll go look for V1 first. So we already know how to do that. I mean, that's like, there's that. Okay, now we know where V1 is. It does not make sense to do a LDBB because LDBB says, I'll get you the first byte of V1. I didn't say anything about accessing the first byte. I said something about getting to member X, sorry, of V1. Now X turns out to be at offset 0, but you should not be using that fact because using that fact means you're optimizing your program, making it brittle. Okay. So now you can do something like this. You can say, okay, since I have the address of member of the entire structure, I just need to load the offset to another register, say C here, and then I can do a add BC, and then we can do a store B and A on the other side, and we are done. So even with this code, you can see how it is a little bit different compared to the previous code. They are different by the lack. The second one has a lack of an LD because V1 is the structure itself. V2 is a pointer to a structure. Yes. Oh, right. Yeah, you're correct. Because we're accessing member X and not member Y. Very good. Thank you. There we go. Okay. Yep. No, it has nothing to do with accessing X or Y. It has to do with what is V2 versus what is V1. V2 is a pointer to a structure. V1 is a structure itself. So that means once I know where V1 is, I already know where the structure is. But if I know where V2 is, I still need one dereference because V2 itself stores the address of a structure. So I need LD in order to get to the actual address of the structure. Yes. hmm Yes, because B on line 32 only contains the address of the structure, not the address of the member that I want to access. I have to dereference B because register B after line 31 is the address of V1, V2 of V2, okay? But V2 itself is not a structure. V2 itself is a pointer to a structure. So that means when I'm done on line 31, B is really a pointer to a structure. Yep, yep, yep. So this means, it is really essential to be able to track the use of registers and correspond the use of registers to the C code that it is supposed to implement in order to say, okay, I can relate what the register has at this point in time to something in the C code because your final exam is all about fixing the assembly implementation given the C code. So you go ahead and then the second. Yep, go ahead. Yeah, V2 contains the address of V1, so yes, they're accessing basically the same thing. Yep, correct. Yep. But I'm using this to illustrate, just strictly speaking, how do we implement each line of code in assembly? So even though they end up really modifying parts of the same structure, yep, yep, go ahead. The final exam is according to our final exam schedule. Okay, so I'm going to segue a little bit here to look up the final exam time. So if you can use a browser, you go to ARC Final Exam Schedule, and this is an evening class. So you go to evening class exam schedule, and then you have to remember, when this class starts, which I think for most people is not an issue, but for people who are habitually late, okay, those people may have to think a little bit. This is a Tuesday Thursday class that starts at 5:30, not 6 o'clock, and our exam date is, oh, okay, I'm looking at the wrong semester, am I not? That is funny. Uh, yeah, I'm future tripping a little bit here. All right, my bad. Where's the final exam schedule? There should be one, sorry, full term. No, the full term does not describe the final exam, I don't think. Nope, it does not. That's okay. Let me go back. No, this one has it too. Huh? There we go. Yep. Why would they put a future semester on the top of this page when this semester is not over yet? When I make a mistake, I blame it on somebody else. Yes. Yeah. What? Oh, let me get this done first. Okay, this is a Tuesday, Thursday evening class. We start at 5:30 p.m. So I think this is correct because it corresponds to the start time of the lecture. So that means because we start at 5:30 p.m., so it is between 5 and 6:25 p.m. on Tuesdays and Thursdays. So our final exam is on the 20th of May. The time is from 5:45 to 7:45, 2 hours. So you might want to put it on your calendar right now just to make sure that you remember. But you guys are not in such a bad situation because the start time of the final exam is actually 15 minutes after the usual lecture time. So most of you, would not have to make any major changes to your schedule to come to the final exam. I cannot say the same about my morning class. I have a class that starts at 9 a.m. in the morning. That's the normal lecture time. The final exam starts at 8 a.m., an hour earlier than the usual lecture time. So I have to warn those students like with extra caution. It's also a beginning class, which means they are still getting used to the way we do things here on this campus. So I have to go like, okay, make sure you write this down. Make sure it's on your phone and wake up earlier that morning. They come in at 8:50, 7 and 9:15 and go like, so how much time do I have in the final? A little less than an hour, yeah. Okay, that was a hand earlier. What was it? Yes. Uh, sure. Is it in academics? Okay. Ooh, yes, it's still not working. What did you do? That's exactly what I'm afraid of. Well, actually, if you want to know more about your program, which is the computer science program, I can probably tell you basically everything that's on the website already. Um, cannot say the same thing about counselors. Well, okay, to be fair, okay, counselors are not specialists in a particular area. They have to know the programs for a lot of different departments and different divisions. So I don't think they can actually memorize everything. I mean, I have been teaching computer science for the past, what, 25 years. So, I kind of need to remember all this stuff. Hmm? Oh. That may be a kind of more individual thing. So I hope it is more of an individual thing. Okay. So now we move on to line 14. No, we are done with line 14. Oh, wait, there's one more thing. Okay, so if you look at this, there's no dereference in between, which means tag. I think we can optimize this, right? Because we added, main v1 to, we added a stack pointer to B, and then we add, C to also to B. Can't we just do everything in one single add and be done with the whole thing? The answer is actually yes. Okay, so the answer is you could roll XX into here so that you don't have to do this. That will work. It will work here, but not before, because before there's a dereference between the two add. This one did not have a dereference between the two add. You basically have two add that are sequential, and they're both just adding some kind of a constant. So you can always fold the constant addition into one single add and be slightly more optimal. We save two instructions basically. Well, yep, yep. So that's two instructions, because one for loading the constant and then the other one for adding. Yep. All right. So we are almost done here. And the next one is, ooh, that looks kind of ugly. Okay. Well, when you see ampersand in the C code, you should rejoice when you want to implement it in assembly, because to get to the value of anything, you have to get to the address first. So address of is actually a freebie in assembly language programming, because you always have to get to the address first. So that means even though in C code it looks like we have to do one extra thing, no. In the implementation in assembly, it means you have to do one fewer things, because you always have to get to the address to get to the value. Because in C, most of the time you're interested in the value, so they don't say, okay, you get to the address, but to get to the value, you need to dereference. No, they want to make it more convenient, right? So that's why in C code, when you see the ampersand, it actually means, oh, it is easier. Hmm. All right, so we're gonna do line 15 of the C code. So after the analysis of the code, you know the dependency, which I mentioned a little bit earlier. Okay, so we get main v2 into A, and then we add AD to get to the address of v2. We LDI B with the offset to um, member. Oh, no, not yet, because it is a pointer. We still need a LDAA to get to the base of the structure itself. Now we can do a LDI B, and that would be X underscore lowercase x. That's the offset to member X of a struct X. And then we just add that to register A. Now we have the entire right-hand side. Offset to V2, the address of V2, V2 itself, which is the address of a structure, offset from the beginning of a structure to member X, address to member X of a structure. Is that okay? Shall I say that again? Okay. Register A has the offset of V2, which is a local variable, which is a pointer. Register A has the address of V2. Register A is V2. V2 is a pointer to a structure, which means A is also the address of a structure, which is the address of the first byte of a structure. This is the offset from the beginning of the base or the first byte of a structure to member X. You add it to the base, which is already in register A of a structure. So register A ends up being the address of member X of the structure that V2 is pointing to. Yep. If you want the value, yes, LDAA with line 44 does exactly that. Um, so at the end, when line 43 is done, register A is the address of V2, but V2 is a pointer, right? So so register A at the end of line 43 is the address of V2. If I dereference it on line 44, then I get the value of V2. The value of V2 is a pointer to a structure. So that means by the end of line 44, register A becomes a pointer to a structure. Essentially, it is the address of the first byte of a structure. Yep, yep. Go ahead. Um, this is kind of the both of these at the same time, because register A had the base of the location, the address of the first byte of the structure. B is the offset. So when you add these two, then register A becomes the address of the member. Yep. Wait, wait, wait. Why do we add B to A? Well, you could add A to B or B to A, because I'm not done yet, right? Because I still have the left-hand side to deal with. Yep. Yep. Go ahead. Mm-hmm. Mm-hmm. What V2 points to? There's nothing inside V2 because V2 itself is a pointer. It points to a structure that has something inside it. Yep. All right. So this is something that we have done kind of already, so I'm just kind of borrowing that template of code, like so, S, T, B, and A. So we are now done with line 15. So it's time to move on to line 16. Okay. So when this is all done, we're going to run it through. Hopefully we have time today to run it through the simulator in Logisim so that we can actually see how the registers are changed. So when you have questions, when you're trying to comment this program to find out, okay, this line is doing exactly this and so on, even if you cannot remember how I describe it and you have just a general idea of, this is what I think it's going to do, you can always verify your understanding following the trace. That is why we have the trace ability, is because the trace actually documents how each register changes its value on a line by line instruction manner. So you can always use the trace to go back and it's like, okay, I suspect that the register has the address of blah blah at this point. Check it. You can always see it. Yes. You are correct. Main V1 and then a Z. There we go. Thank you. All right, line 51. We are moving on to the last line of the C code. So this time I'm going to go a little fast, just so that I can kind of finish this entire thing and get it to run. So this is LDI a main V2 add AD LDAA LDIB with XX add AB LDAA, and then we deal with the left-hand side, which is actually easier because this is just LDIB with main V3 X underscore X plus add BD STBA. All right. Okay, so I think we are done with this entire program right now. LDIA 0 to return the 0 to the entry code. All right. So before we run this program, we kind of need to figure out what is going to happen to it. So the way that is going to be done is looking at this and go like, okay, what should go where? All right. So V2 is the address of V1. So that would be, let's see, this is FF, E, I cannot count backwards in alphabet. So this is FF, and let's just see how many times we have to subtract. 1, 2, 3, 4, 5, 6, 7. F minus 7 is 8. F8. So that should end up as F8. Okay, 0x F8. All right. And then we put a 20 to what V2 points to. So that would be this one should become 20, which is 1 4 in hexadecimal. And then the X here would again end up with a value of A because that's 10. And then v1.z is going to get the address of its own X. So that should be F8 also. And then v3.x is going to get the same value, not address, of where v2 is pointing to, or the member x of what v2 points to. So that should also be an A over here. These two are not initialized, they're not touched, which means they really should be 0, but they're basically essentially not touched. They're not initialized. So let me do some last minute counting here. 8, 9, a, B, C, D, E, F. So I think they all work out. All right. So, yep, go ahead. Um, well, that's a very rhetorical question. Yes, you can, because there's such a thing called typecasting. So you can always tell the compiler, don't complain. I know what I'm doing. Just let me do it. And C++ will let you do it if you typecast it. So yeah, you can store at whatever you want at Z, but properly, it should be the address of something. It will treat whatever it has as an address. Yep. But only when you dereference. Only when you use it as a pointer, when you dereference it. Yes. Question? They are allocated on the stack. They're allocated on the stack because of the way I define the labels at the beginning here, and also because of how I use LVS to allocate, and also to deallocate at the end here, where wait, wait, right here. This is the deallocation. All right. So yeah, say again. Okay. So let me try to finish this first, and because I think we are all running out of time, sort of. But I'm gonna finish this. So we'll go to hmm? Oh, you got it. Okay. Cool. And then we just submit struct dot ttp asm. And I still have to extend today's the lab until today's 8:20. So, even if you leave the classroom early, it's not going to do you much good. So let's go ahead and get this done first. Okay, there we go. And this program is pretty short and easy. Okay, that's correct. I think that is correct. Okay, so let's double check. Um, this is what location? 8, 9, AB. So that is correct. Um, F9 is 1, 4. So this is 1, 4 right there. That is correct. F8 gets 0A, that is correct. And then FA gets F8. So this is 8, 9A. Okay, getting F8 here is correct. And then FC get 0A. So that's 8, 9, A, B, C. That's getting 0A. So they all checked out. So the program is in fact implemented correctly. I will send it to you as an announcement. Okay, so you know what to do with it. It will take you some time. Okay, but that's basically studying for this class, is to go through this code, go through the trace, and as I said a little bit earlier, column C, column D, sorry, tells you how the registers are getting updated. So every time I said, okay, by this time, register blah blah should get the address of blah blah blah, you can check it. Okay, you can even go backward and say, how did they get that address magically? Well, nothing is magical. You just have to step backwards and find out how did we calculate the address to put it into that register. Okay, so the trace gives you the ability to execute the code backwards, which I think is really helpful when you try to understand how things work. Alrighty, so now we can go back and kind of change the due date of the lab that was assigned a little too early on the 22nd. So let me go ahead and change this. And you can probably just go, just remember the access code is struct. By the time you get to the lab, I should be done editing it. So I will see you in the lab. If you have done this already on Tuesday, you're good to go, or do whatever you want in the lab or otherwise. Hmm? No, I cannot really fix it because I cannot tell how many characters it can store. The problem has to do with Canvas cannot store a really long string as a solution, and the actual answer is longer than what Canvas can handle. But I can grade that manually. Yeah. Fibonacci? I thought we worked on that on Tuesday. Oh, but I never sent it out. Oh, okay, I see. Yeah, I can do that. All right. Okay, let me. Yeah, my recorder is still recording.